First, water, when it transforms into a long, heavy wave, can transport entire cities, with tsunamis being the prime example. In the deep ocean, such a wave is almost invisible. Its height is barely perceptible, but its length spans hundreds of kilometers, and its speed rivals that of an airliner. However, near the coast, where the seabed rises sharply, the wave compresses, loses length, and stands up, becoming a wall that carries a mass of water, mud, rebar, boats, and cars like a flow of rubble. In 2011, off the coast of Japan, water elevations exceeding 40 meters were recorded in some areas, the height of a 14-story building. Meanwhile, the drawback preceding the impact is a characteristic yet treacherous signal, sometimes exposing the seabed for hundreds of meters. An even more striking illustration of this power is the 1958 Lituya Bay, Alaska megatsunami. A giant landslide crashing into a narrow fjord propelled the water with such force that the waves stripped trees at an elevation of about 524 meters above sea level, leaving a bare scar on the slopes, still visible today. It's also important that tsunamis aren't solely caused by earthquakes. Landslides, volcanic eruptions, falling ice masses, and even meteorite impacts can generate similar impulses. Modern buoy networks and satellite algorithms improve early warning, but physics remains unforgiving. Near the coast, the interval between the jolt and impact is measured in minutes, not hours. Water doesn't burn or tear, but its mass subjugates everything. Destruction is created not just by crest height, but by the pressure and momentum as tens of millions of tons surge through streets, turning asphalt into riverbeds and buildings into loose debris carried further than imaginable. Second fact: the inability to compress water with bare hands creates an illusion of softness, but in technology, it acts like a razor and a sledgehammer simultaneously. Water jet cutting is a cold method where a jet under pressure of up to several thousand bar is accelerated to speeds close to a kilometer to the second, and upon meeting garnet sand, cuts through steel, ceramic, and bulletproof glass as if slicing wet cardboard. Where pressure and speed are extreme, cavitation occurs, sudden boiling on a microscale. Vapor bubbles form in a fraction of a millisecond and immediately collapse, hitting the metal with microjets and shock waves, leaving craters and pits as if the surface were chewed by invisible teeth. On ship propellers, such bites grow into holes, reducing efficiency and loosening hulls through vibration. On hydroelectric power plant turbines, cavitation does in hours what corrosion would do in years. An illustrative episode is the high spillways of 1983 at the Glen Canyon Dam in the USA. The flows tore out chunks of concrete in the spillway tunnels until engineers installed aerators to soften the bubble collapse. In household pipes, a similar enemy manifests as water hammer. The instant closing of a faucet slams the water, and this shockwave seeks a weak joint, capable of breaking a weld or ripping off a pressure gauge. The same laws explain both the fragile sand at the base of waterfalls, where bubbles crush rock, and the wear of injectors in engines, where fuel under high pressure behaves almost like water, machining steel. A silent liquid, under the right conditions, acquires the character of an industrial cutting tool and a battering ram, precisely due to its mass, speed, and instantaneous pressure changes. Third fact: a hurricane rarely kills with wind. Water becomes deadly when wind and low pressure turn the sea into a slow battering ram. Pressure drop in a cyclone center acts like a giant piston. For every hectopascal drop, the ocean level rises about a centimeter. Added to this is the wind's effect, pushing water towards the coast and into river mouths. If the shelf is shallow, like in the northern Gulf of Mexico or the Ganges-Brahmaputra Delta, the effect intensifies. The surge wave stretches for miles and advances like a flat bulldozer. In 2005, Hurricane Katrina caused an 8 to 9 meter water rise on the Mississippi coast. In 2013, Typhoon Haiyan flooded Tacloban, Philippines, with 6 meters of seawater and debris. In 1970, a cyclone storm in the Bay of Bengal pushed water onto the low-lying islands of East Pakistan so quickly that hundreds of thousands of people are estimated to have died. The trick is that the Saffir-Simpson scale measures only wind, while actual destructive power is better described by the storm's integral kinetic energy and coastal geometry. Funnel-shaped bays, astronomical tide surge, and river flood combine to create compound flooding, where water comes from below, above, and the sides simultaneously. Add to these meters the surf and the single plop of a long wave, and a single-story house's attic is underwater, its beams later bearing seaweed and shrimp nets. The sounds of such a surge differ from storm movies. Not winds roar, but a low hum and scrape, like an entire furniture warehouse being pushed across asphalt. Most dangerous is the acceleration. When water crests a dam or levee, it becomes a swift flow, with hundreds of kilograms per square meter of pressure, sweeping away slag blocks, ripping out piles, and behaving like a river at street forks, finding a new course where a city once stood. The fourth fact concerns water flows that look not like waves but like avalanches, dense, heavy, and fast. Lahars, volcanic mud flows, are born when ash and debris mix with water from glaciers, lakes, or torrential rains, turning into liquid concrete. On November 13, 1985, on Colombia's Nevado del Ruiz, a small magma eruption under the glacier was enough. Hot pyroclastic emissions melted the ice, and lahars, at speeds of up to tens of kilometers per hour, burst down river valleys. The city of Armero, located 70 kilometers away, was buried at night under a 4-meter mass. Over 20,000 perished. Such flows have a higher density than water. They carry boulders, logs, rebar, and accelerate in narrow sections like nozzles. Bridges collapse like children's toys, and the riverbed after passage becomes higher than the surrounding fields. So much material is brought by one episode alone. Relatives of lahars are glacial lake outbursts, when the natural dam of moraine or ice cannot withstand it. Icelanders gave this phenomenon their own word, jökulhlaup. Subglacial reservoirs accumulate water for months and then release a discharge comparable to a major world river in a single day. In 1996, such an outburst after a subglacial eruption swept away bridges in southern Iceland, and the peak discharge was estimated at tens of thousands of cubic meters per second. In the Himalayas in 1985, the sudden release of Lake Digcho destroyed a hydroelectric power plant under construction. In Peru and Nepal, similar lakes today regularly monitor the valleys, and engineers install siphon pipes, flushing lakes to a safe level and building early warning systems. The scale of this power is understandable from geology. During the Ice Age, catastrophic outbursts of the ancient Lake Missoula, according to estimates, released volumes such that on the Columbia Plateau, Gigantski Ribi, house-sized undulating ridges left by the receding water wall, are still visible. In the liquid disaster, there is no rocket fuel, only mass, slope, and gravity, but sometimes that is enough to rewrite the map in one night. Fifth fact. For a long time, killer waves were considered a sailor's tale, but the ocean responded with instruments. On New Year's Day 1995, the Danish platform Draupner recorded a solitary wall of water about 25 meters from trough to crest, sharply higher than the surrounding significant wave height. Such a wave is called anomalous if it doubles the average level for that storm. And it's not about fantasy, but about the statistics of rare events and the physics of summation. Wind blows the sea by a set of waves of different lengths. And once the phases of several crests coincide, constructively summing into a pyramid. Narrowband spectrum intensifies nonlinearity. The so-called modulo instability develops, where energy merges into a single king impulse. An additional focus is created by currents. In areas where opposing flows like the Agulhas current slow down the incoming storm swell, wavelengths shorten, steepness increases, and the formed crest becomes formidable like a jackhammer. Unlike tsunamis, these waves, born of wind and statistics, appear in open ocean without precursors. They are short in length, but steep, with a vertical undercut that crashes onto decks and portholes from the height of a multi-story building. In recent decades, satellite radars and buoy networks have collected dozens of reliable fixes, and captains' reports have received technical confirmation. Bridge windows, installed at dozens of meters high, were blown out, and bow superstructures, designed for a normal storm, received a volley of green water, a continuous flow that bends handrails like wire. Design norms for ships and offshore platforms now account for the probabilities of such outbursts, and wave forecasts now include products about the probability of velvet waves, rare but real. The sea doesn't have to be smooth, even within chaos. Sometimes it stacks all domino bones into one tower, and this tower, albeit for tens of seconds, becomes the most powerful wall of water on the planet within a radius of hundreds of kilometers. Sixth fact: tides are when the moon and sun, without touching the water, lift and lower entire seas. The power here is shown not in the height of the crest, but in the tonnage that is repeatedly moved according to a schedule. In the Bay of Fundy, where the bay's geometry resonates with the semi-diurnal tide, the water level range reaches, by various estimates, up to 16 meters. The bottom in the morning is dry land. In the evening, it is a deep fairway, and vice versa. Where the tidal wave is forced into a narrow channel, it breaks into a hydraulic jump, creating a bore, a front wall running up the river. On China's Qiantang River, it was nicknamed the Silver Dragon. In half a minute, the calm surface turns into a boiling ridge rushing forward at the speed of a car, and each river bend responds with a dull roar. The Amazonian, Pororoca, rumbles in the mangroves, cutting bushes and roots. Here, after its passage, a fresh line of breakage remains on the banks, like a chalk mark of the water level on the wall. In narrow sea straits, tides gather speed into a stream. Norway's Saltstraumen pushes volumes comparable to hundreds of millions of cubic meters through the strait twice a day. And at the peak of the current, whirlpools spin like industrial mixers. These are not holes in the sea, but nodes of speed shear, where the surface layers tear and twist into house-sized donuts. Fishermen and pilots know the minute-long windows of dead water between high and low tide. When the flow subsides, miss them, and even a powerful engine will drag the boat in place as if it were on a rubber band. This same force is an engineer's dream. Tidal power plants place turbines in the span. Water works back and forth like the planet's giant breath. But engineering poetry is next to danger. Jumpy levels pull on anchor ropes, tear poorly secured piers, and coastal erosion with accelerated streams gnaws at clay and sand, drilling bowls at the base of retaining walls. Whirlpools and bores seem like miracles, but they have an exact touring schedule. Moon phases, depths, riverbed shape, and it is precisely for this reason that they are so merciless. They arrive on time, but leave taking everything in their path. The seventh fact is that water has a secret way of moving mountains while remaining invisible to the eyes. Underwater mud avalanches, or turbidity kinds. This is not a coastal wave or a tide. It is a suspension of sand, silt, and debris that, having become heavier than the surrounding water, creeps down underwater slopes like liquid concrete. Such a river in the ocean can rush at speeds of tens of kilometers per hour, carving canyons in the seabed as deep as a skyscraper and extending them for hundreds of kilometers from the shore. The most vivid evidence comes from cable stories. In 1929, after an earthquake near the Grand Banks of Newfoundland, an underwater flow successively cut off a dozen telegraph lines. The cutoff time of each allowed engineers to calculate how fast and far the avalanche traveled. Almost a century later, similar episodes hit modern fiber optic routes. Powerful flows of murky water from the mouths of large rivers and collapses on shelf slopes have triggered long turbidity marches, which for days moved along underwater canyon beds and tore cables at depths of kilometers. These same flows bury subsea pipelines, drag platform anchor systems into lowlands, and deposit distinct cakes of sand and silt. Geologists call them turbidites, and by their layered signatures read past catastrophes as if from cores from the planet's archive. An important detail in their mechanics: the denser the suspension, the more stable it is, and the longer it retains its inertia. One push, an earthquake, a landslide, an eruption, or an extreme flood, and the entire mass breaks loose, turning the continental margin slopes into a giant ski slope for mud. And though on the surface it is calm, in the depths a kind of reverse tsunami is happening. Not a wall from above, but a heavy flow from below, which can halt a whole region's internet for an hour and rewrite the ocean floor's relief so that new canyons will later be followed by the next avalanches. Fact 8. There are waves that are almost invisible, yet taller than a skyscraper, internal waves in a stratified ocean. A warm, salty, light upper layer lies on a cold, denser lower one. The boundary, the thermocline, acts like an underwater surface, and on it run waves with amplitudes of tens or even hundreds of meters. In straits and on slopes where the tide compresses and stretches the layers, solitons are born, solitary humps that travel at car speed, kilometers long. In satellite images, they read like long zebras. The alternation of dark and light bands is the trace of compression and expansion zones, where roughness changes and films of surface substances gather. Behind this graphic is brute force. An internal surge onto the shelf causes an underwater waterfall, overturning the water column, lifting nutrient-rich waters to the surface, and instantly changing the thermocline. Divers feel a cold knife run down their skin. The helmsman sees only calm water, but at that depth, platform cables and anchor lines receive sharp, pulsating loads. Autonomous gliders and buoys are blown off course, and a submarine can be lifted or dropped tens of meters in minutes. At points like the Luzon Strait, these waves are like scheduled guests of the moon. Every night, they shoot out in packs into the South China Sea and run for hundreds of kilometers until they break up into a train of smaller crests. Overall, this phenomenon has two sides, a dangerous one for engineering and navigation, and a creative one for ecosystems. Internal waves feed the seas. Their mixing triggers blooms, drives feed to plankton, and fish and birds follow. But if you are installing a platform, laying a cable, or planning dives, you cannot ignore this invisible relief power of water. The ocean may be calm on the surface, but underneath a true mountain range of moving density unfolds. Ninth fact: water can rebel without an earthquake. The very shape of the shore and the whims of the atmosphere create gigantic swings in bays and lakes. These are seiches, standing oscillations of the level when the entire body of water begins to slowly slosh from one end to the other, like soup in a pot after a sharp jolt. The jolt is given by gusts of wind or pressure jumps. An atmospheric ridge walks over the water, and if the speed of the disturbance is close to the speed of a long wave in this body of water, resonance occurs. Each new impulse will hit in rhythm and rock the surface by meters. Narrow bays and long lakes are particularly vulnerable. Against the wall, there is a belly with maximum amplitude. In the center, a node with an almost stationary line. Thus were born the sudden blows on the Great Lakes, when after the passage of a storm line towards Chicago or Duluth, the water receded from the embankment in minutes and returned as a continuous step several meters high. In the seas, a relative of the seiche acts, the tsunami, a long wave from a barometric wave and a squall, which is driven into bays and marinas. In the Balearics, it is known as risaga. On a calm day, the mooring lines begin to sing, yachts bump dully against pontoons, and level markers draw sawtooth patterns, tens of centimeters per minute, sometimes meters. On the Adriatic, a similar marobio repeatedly catches fishing ports off guard. The sky is blue, but in the bay there is a gray, boiling escalator. The danger here is not in the crest, but in the repetition. After the first surge, a rollback follows, then a new rise, and so for hours. Mooring lines break, bollards twist, boats converge and diverge like scissors. The water, like a giant pendulum, seeks balance and does not find it. Engineers fight resonance with the geometry of moles and dampers. Meteorologists set up dense barometer networks. But the cunning lies in the breadth of triggers. A storm front bouncing off tens of kilometers away. A pressure jump in a cold front. Phase coincidence with a tidal long wave. Unlike a tectonic tsunami, there is no jolt here after which everyone awaits the wave. Here, the conductor is the air, and when it plays the right note, the entire body of water responds with a deep, very material bass. 10th fact: the most dangerous and laborious currents near the shore are often not visible on a postcard. Rip currents and longshore drift quietly reconfigure coastlines, moving millions of tons of sand and take away people who mistook a smooth path for a calm spot. The mechanics are simple and ruthless. The surf pushes water ashore, the bar near the shore holds it, and the excess mass seeks an outlet. It finds a gate between sandbars, near a pier, or in a channel, and shoots into the sea in a narrow stream. The speed is like a strong swimmer's and higher. On the surface, it's a matte strip without foam, in which ribbons of algae and foam stubbornly stretch away from the shore. It's not a whirlpool or a pulling bottom. It's a horizontal pump that extends for tens, sometimes hundreds of meters. And only then does the current dissipate, and only there can one safely move sideways. In parallel, the obliquely incoming swell sets in motion an eternal conveyor, the longshore drift, which cuts away the coastal edge, digs channels near one village, and builds a spit in the next. From here grow long spits and barrier islands that migrate meters per year and shift in the leaps during storms. A night's overwash throws a tongue of sand over a dune, and by morning the map is already different. The Curonian Spit, the deltas and lagoons of the eastern Baltic, the skerries of the North Sea, all live in this balance of transport. Protective dams, groins, and breakwaters merely redirect the flow, accumulating sand on the leeward side and exposing gravel on the windward side. Any new harbor changes neighboring beaches, like a stone in a mountain stream changes the currents. On one side, a quiet pocket, on the other, an accelerated stream and erosion. And this quiet machine is more powerful than a single storm. One storm roared and left, while rip currents and the longshore conveyor work almost every day, meter by meter reshaping the landline. For humans, this power is insidious because it looks like calm. It's recognized by the pattern of foam, by the narrow road between the whitecaps, and the only smart strategy is to exit the current sideways, not to fight the pump head-on. Thus, water, in the absence of any explosions, slowly and by instruction reworks the continent, without asking permission.